Today we'll be talking about feature engineering. I think it's a very, very important aspect of machine learning. A few things about me. I work as a competitive data scientist for H2O. As you may know, H2O creates software for predictive analytics. My role is to make certain that the tools, the software is as predictive as possible so we can get very competitive results. And I've done my PhD in machine learning, specifically in ensemble methods, as in how we can combine many different models in order to get better results, better predictions. And I have done a lot of Kaggle. I presume most people know what Kaggle is. It's this platform that hosts machine learning challenges where people compete for prizes, and they have a ranking system as well. So I have been able to be #1 in this platform, and I'm still currently 3rd. But what I really take away from this is I have been able to participate in more than 180 challenges, close to 200, and some of these problems are very diverse. So like image classification, NLP, time series, tabular data optimization problems. So I have been able to see what works and what doesn't in different problems. From a machine learning, from a feature engineering point of view, modeling and other aspects. And hopefully I have been able to also introduce that and make our tools in H2O better. This is my role. Many of the slides I have prepared today, much of the source material is inspired to my colleague Dimitri Larko, who is also a Kaggle grandmaster. I need to give credit where credit is due. So that's it. That's it about me. This is what I want to go through today. Very briefly, I want to mention about what is feature engineering, why it is important, and then we will dive into different categories of feature engineering. We will start with categorical encoding, which is very popular and very important to get better results. Then we'll go through numerical encoding, as in how we change numerical fields in the data. We can see some cases of how we can handle missing values for the previous 2 types of encodings. Very briefly, we will look into interactions, how you can combine 2 features to create one that can potentially give you higher accuracy. We will look also a little bit into time series, and very briefly also see NLP and images, high-level things we can do so that you're aware what kind of techniques or what is the main idea when you have to handle this type of problems. Feel free to ask any questions. I have managed to log in with 2 screens. So in the other screen, I'm able to look at the chat. So if you ask any question, I might be able to see it in real time and come back to you. So feature engineering, why it is important. I have some quotes from some quite well-known people in the machine learning space. Andrew Ng says, coming up with features is difficult, time-consuming, requires knowledge, but then emphasizes machine learning is basically feature engineering. And I think we can all agree that feature engineering is very, very important in extracting information and make it better for to solve specific machine learning tasks. But what I really like is the quote from Saint Miel. Maybe I'm not pronouncing his name right. I hope he can forgive me. But you have to turn your inputs into things the algorithms can understand. And I think that is a very, very important point, because most algorithms understand numbers, for example. They don't understand letters. So imagine you have text or a field that has letters. You need to find a numerical representation that contains the knowledge, that contains the information, in order to be able to apply machine learning and apply different tasks. It's very important to find a representation that the algorithms can understand. And sometimes there are multiple ways to do this. So trying to find the best way to do it can be of the essence in order to maximize the accuracy in a specific problem. I want to give an example, high-level example, why feature engineering might be important. So here you can see I have two features, X and Y, and I have a classification problem, two classes, you know, one with the blue dots and one with the red dots, and you can clearly see they're separated. But for example, if I try to use an algorithm, a linear algorithm that tries to find a linear relationship, tries to separate the two classes with a single line, it's not very easy. It's impossible, basically, to do it with the current feature set. And a lot of the algorithms we use or we start with when we try to solve the specific problems are linear, like a linear support vector machine, for example. So in reality, what we want is an algorithm that is able to use that circle. But in reality, what we do in machine learning is we try to find a different representation for the data in order to make a simple algorithm or any given algorithm to give you the results that you want. For example, in this case, I could use polar coordinates, which is this technique where I can use a reference point and create basically a new pair of X and Y, taking the range into account and the tangents. And I can then transform my X and Y coordinates into these P and theta coordinates that you look on the left side of the screen, which then are easily separated with a single line. And this is the power of feature engineering. You see, I have something, but then I find a way to transform it and I make it easier for specific algorithms. And you should know that each algorithm has strengths and weaknesses, right? It may be that if I wanted to use a different algorithm, that wouldn't have been a big issue. But in this case, making this transformation makes it very easy for an algorithm that can fit linearly to find a separation and give us a perfect classification in this point. So hopefully this can help you understand why we want to find a representation in the data which can be more suited for specific tasks. In machine learning, we have many different types of problems, and on high level, I can say, you know, image classification or computer vision problems, signal processing or sounds, NLP, time series, tabular data, other types like general optimization or as in linear programming or recommender systems, for example, multiple different problems, and each field has its own feature engineering. I don't want to get too worked up with what I'm showing on the screen right now. We will go into more detail with some of these categories, but the main point I wanted to transfer across is that, you know, it's different problem has its own different feature engineering. So you just need to become familiar with what techniques I need to use when, for example, I have to deal with an NLP or text classification problem. And the kind of things that I will be using there are different than, for example, when I try to deal with a time series problem, when I have temporal elements in the data. And then again, it will be different than when I try to handle images or sounds, as in signal processing, different with numerical and categorical features. So now I think we can go into the first category, the first type of feature engineering. It's a very popular one. It's the one that is applied on categorical features or nominal features. These are normally features that in your data are represented with words, for example. You obviously can have other representations. In any case, they are not continuous features or ordinal, for example. There are multiple ways to convert the categorical features. And again, algorithms understand numbers. They don't understand letters in most cases. So you need to find a way to transform this in order to get the most out of the algorithms. And on high level, I will show you some of these transformations. So consider you have a field which is called animal, and it can take certain unique categories. So in this case, dog, cat, and fish. These are the unique categories that this categorical feature takes. So one way to transform this is to use frequency. So just count how many times each animal appears in the data and basically replace with this value. So dog appears 3 times, cat appears 4 times. So anywhere I see a dog, I replace with 3. Anywhere I see a cat, I replace with 4. Then you have a feature that shows how popular its category is. So you have, it is a measure of popularity. And sometimes, especially if you have lots of different categories, this kind of representation can be quite powerful and contains a lot of predictive power. And there are ways to scale that. So even than just taking the raw count, you can also divide with the total counts in the data. So you basically have a proportion, probability, not just a frequency. Another way to do that is to use label encoding. That's a lazy method where you just find the unique categories. In this case is cat, dog, and fish. You sort them alphabetically, and then you assign a unique index. So this transformation, some algorithms are fine with this type of transformation, although you assume there is a relationship with how this with the you know, that it based on the alphabet essentially, which might be wrong. But you know, some techniques like you know, LightCBM or XGBoost, you know, they should be able to figure this out, especially if you don't have many categories. Most of the times it can be used as a preset for another transformation. For example, we can then go on and create what we call one-hot encoding or dummy coding, which essentially means we take the unique categories and we create binary features. For example, is it a dog, 1 or 0? Is it a cat, 1 or 0? Is it a fish? And so forth. Another thing we can do, so the dummy coding is quite a useful technique. One issue with it is that if you have many categories, you may be increasing the dimensionality, as in the number of columns, by a lot, which can make it difficult for some algorithms to give you good results and find significant features created in this way. Another way to do this is to actually utilize target information. So in this example, let's assume I want to predict something like cost. So in this case, cost is what I try to predict, and I can create an average, I can create basically a mapping that estimates for each animal what is the average cost based on the training data. And I can then essentially replace with these values. So instead of having a dog, I can have what is the average cost of the dog. And you know, if I try to predict the cost, then I have already a mapping that I have already a feature that directly maps the target variable, which in this case is the cost, and may make it easier for algorithms to extract the signal and predict the target. This technique can be a bit dangerous because you can introduce leakage. You need to be very careful about how you use this. And going forward, I'm going to explain some different variations of how you can do this in a way that you can minimize the leakage, because then you can actually overfeed quite a lot and have compromised results. But if this is done right, this is potentially one of the best techniques you can use to quickly squeeze the information that the features have in relation with the target. So one way to do this to create this target encoding type of feature is to calculate the average of the target based on how many counts you have for each category. For example, have 4 categories. In these 4 categories, 75% is 1, for example. But then also introduce what we call a global parameter. So if you calculate that the average of your target is, for example, 0.77, then you can also add a weight to that. So what you can basically say is, I'm taking always the average mean target that I know from an existing category, but I'm also regularizing it based on my global average out of all the rows in the data. Let's show a specific example. For example, as you can see here, I have feature that takes values A, B, and C. And if you can see in A, I have 3 1s and 1 0. So this will make my target 0.75. But then if I calculate in my all the data set, then the target is 0.77. So basically, I'm giving the weight of 4 because I have 4 counts for the A feature and the 0.75, but I'm also giving 2 counts to the overall mean of the dataset, which is 0.77. So I get a value which is not 0.77. It also leans a bit towards to the average of the dataset. And you can see this as a form of regularization, as a means to not over-trust the results you see from your training data, which may be derived from a small number of cases like here, and also take into account what's happened in the whole data set. And if I increase this A parameter, which puts essentially more weight to the average target of the whole data set, then the results will be even closer towards to that average of the whole data set. And this is a good way to prevent leakage, but at the same time, do take into account that, for example, a category has indeed 0.75 chance to yield an outcome of 1. So to take that information. And here I'm just showing how the relationship changes for the previous 3 cases once you increase this A parameter. So you can see the higher A parameter you put, as in the higher weight to this global average, the more your results will lean towards this average of the data set, which in this case is this 0.77. Another way to do this is to introduce noise. So if I was to use the mean encoding as it is, I would replace A with the total average that I see based on the data. So 3 out of 4 are 1s, so the mean encoding as 0.75. However, this can introduce leakage because I'm using all the rows in the training data. And when I essentially replace with this, when I create this value, this includes this row. And if I don't have a big enough count in the data, this can be a bit compromising. Imagine if you have only 1 row, for example, then you know that 100% this is going to be 1, if the target is 1. So you already give away the answer. You don't let the algorithms trying to figure that out. And this can create a very weak model. So one way to overcome this is to always exclude or leave 1 out when we try to create this type of target encoding. So as you can see here, for the first row of A, I will use the remaining rows in order to estimate my average for that row. So as you can see here, I have 2 1s and 1 0. This is roughly 0.66. So I will actually create a new feature that in the first row, it will have the value of 0.66. Now, when I replace, when I create the feature for the second row, I will use the remaining values. And in this case, it will be 1 because all 3 other values are 1. Following similar logic, this one will be 0.66 because the other three cases are 2 1s and 1 0. Then I go to B. It's pretty much the same logic. Hopefully you can follow up. Moving on to the next type of transformation. That's one way to do this. But sometimes if even that cannot fully protect you for leakage, especially if you have many categories with low counts like the one you saw before, another way to do this is to also shuffle the data randomly. So after you shuffle the data, you get a representation like this. And when you start encoding, for the first case of B, you don't have any previous known value for B. You see, you start from top to bottom. So you basically replace with the average of the whole data set, which was 0.77. And the same goes for when you try to replace the first A. There is no previous known A, so you're going to essentially still put the average of the data set. But now that you go to B, you already have a previous known B value, so you can create the average based on the B values you have seen so far. So in this case, you have one B value that was 1, so you essentially replace this value. And even you can even do some mixes here. In reality, this doesn't need to be just all the B values. You can still regularize with the total of the total mean of the data set, like how I showed you before. But just to follow up this example, in this case, we don't use the total mean of the data set. So because this is the second B I encounter, I use the average of all previous Bs in regards to the target. And because I only had one value with the outcome of 1, the value is 1. And same is for the first A. Sorry, for the second A, because the previous only A had 1, average is 1. But that changes when I encounter the new A value. Now I have seen 2 previous A values that have an average of 0.5, so and 1 and a 0. So this is how it follows the same logic. This is how you can essentially encode the this feature, introducing this bit of noise in order to make certain that you don't compromise your results. You never include information when you recode this feature that comes from the same row. So now let's move on to some potential transformations you can try to numerical columns. Some of the things that you can do is, with numerical features, you try to capture non-linearities. So we will see how you can do that using binning techniques. Another thing you can do is dimensionality reductions using techniques like singular value decomposition or principal components analysis. You can also apply clustering. You can create features from cluster IDs or distances from certain clusters. You can do scaling or normalization, or, for example, you can use some univariate transformations. So if instead of using the feature as is, you can take, for example, the natural logarithm of a feature. Someone is asking, by the way, as soon as I see a question, I will reply. Someone is asking if outcome is continuous, how mean encoding with noise work. Pretty much in the same way. You still have an average of the data set, and you still have an average based on your existing categories. So the logic actually doesn't change. Before you had the 0.75 because your target was ranging between 0 and 1. Now you may have 30 or 40. The logic is pretty much the same. Nothing changes. You still take mean of your existing categories in relation to the target, and you still have a mean that is derived from your whole data. So you can pretty much apply the same calculations that you've seen before without having a binary or categorical target. You can still do it with a numerical one. So moving forward, let's have a look into binning. I may have a feature which is called age. It's very, very popular one. And then I want to use age in order to predict income. So income is my target. And quite often when you see that relationship, and this is actually a well-known relationship, income increases a lot in the beginning as age increases. When you reach middle age, income still increases, but with a lower pace. And then once you get to retirement or close to that age, then income starts decreasing. So it's not a straightforward, it's not a linear relationship, it's a relationship that has bumps. This can be a bit tricky for certain algorithms that have certain assumptions, for example, a linear regression, to capture this. So what you want to do is to capture these points, these cutoff points, where that relationship between the target and what you try to predict essentially shifts. And one day you can, then you essentially transform your numerical features into categorical. Here I give a sample of categories you may be using. So then you transform your numerical feature into categorical. And this can be quite important for certain algorithms in order to be able to capture these shifts. So the how you find these bins, one way to do it is to just use quantile binnings. So bin it based on proportion. I'll take the first 20%, create a bin, second 20%, and other bins. And another way to do it is, for example, to use decision trees. Decision trees by default, the way they work is to try to predict the target, finding the best ways to cut, to chop essentially a feature, so they can give you back these cutoff points that seem to be the most predictive, that seem to contain the most information. By the way, I have received a question here. Is it data that drives the feature engineering or the problem we are trying to solve, or is it a mix of both? I would say it's a mix of both. I mean, clearly in some problems like image classification, by default, there are very different things you would do to an image than you would do to text, right? However, it's not like in every tabular problem that that target encoding would work. I've seen that in some cases, dummy coding, more one-hot encoding would work better. Similarly, there may be image classification problems where rotations might not work, for example, or resizing the image may not work. You need to leave the image as default. So it is a little bit of both. It really, there are certain transformations that are more likely to happen in certain problem, but then, you know, it's not like once you know the problem, you definitely know what it's going to work. You still need to interrogate the data. You still need to try different techniques and see what works. And in most cases, from my experience, it's very tough to get that intuition. You actually have to try lots of things and see what works best. For example, in your validation data and some holdout data, you actually need to try it out. It's quite tough to work with intuition only. Another type of transformation what is common with numerical features, and I have an example here using this iris data set, which we try to predict this class of the plant, and you have some features. So what you can see here is I have 4 features and 3 classes. If I use 2 of the most predictive ones, sepal length and sepal width, I don't get a perfect classification, but you can see I'm still able to separate like the red category from the rest. And then the orange and the gray are a bit mixed, so there is not perfect separation. But still, these 2 features are quite predictive. But if I was to use a principal components analysis, which can take the given data set and through a set of matrix routines, it can actually, using the eigenvectors, you can reduce it. You can summarize this information with less features, for example, with 2 components. I can create 2 new features out of the 4 given ones, where if I try to plot them, now as you can see, I have a much better separation. So I have been able to compress the information from these 4 features into 2 ones, which then, it can clearly give me a much better way of separating the 3 classes. You can see now I have less mix of gray and orange bullets together. Another thing you can do is clustering. And I'm a bit cautious about time, so I won't be going too deeply into the different techniques, but it is pretty much the same logic. I can try to to classify the rows into certain buckets. For example, I could use a k-means clustering, and without knowing what the target is, without providing that information, I can just then output the given cluster, and here you can see that there is 3 different clusters created, and that's an algorithm that doesn't know the target class. It hasn't seen it. It was only able to create these 3 different classes. So it tells you that a single row in the data belongs to one of these clusters without knowing the actual class. And if I actually plot the class against these 3 features, you can see how similar they are. This is actually very close. So without knowing the target information, just by seeing which rows should be more similar to each other, and through comparing the rows together, I can create a representation that seems to be quite close to the actual distinct classes that I have in my target variable. So you can see how you can derive information that might be useful for modeling, even without providing information for the actual variable that you want to predict. By the way, I have received a question: how to know which encoding technique is efficient, is based on output accuracy? Is this any metric tells? How can we tell about efficiency? I'm not sure what efficient exactly means in this case. Most of the times, a target encoding can be, for example, more computationally expensive and more memory expensive because you need to store these mappings. And you can imagine with some problems with million distinct categories, and I have seen this kind of problems, this can actually be quite heavy for production. So there's something to think of there. But if you were to base the decision on accuracy, then this is indeed, most of the times I make the selection based on accuracy. So I have a holdout data set, I try different techniques and to see how they perform on that holdout data set. And this is how I base my decision. But if I indeed need to take efficiency into account as a speed or memory, then it may be that some transformations like dummy coding or target encoding can be both more computationally expensive and more memory intense. So this is something to think about when you try to build something that may be put into production. Another technique that that could be used is scaling. And I have this iris data set that I have just added a random feature. And that feature, as you can see, has very, very different range, very big values compared to other features. And this can be a problem for machine learning. It can be a big problem because certain techniques may not converge when you have a feature that has very, very different rates than the rest. So primarily from a convergence point of view, you may want to consider scaling. For example, a way to do this is to just subtract the mean divided by the standard deviation for each column, and then you get something that is basically on the same space as you can see the transform frame. So you may want to consider this if you want to use techniques like linear regression or neural networks, which may be using some algorithms like gradient descent, which can be very sensitive to when the input range of the features is not it's not on the same space, it's not on the same level. So moving on to missing values, this is a type of transformation, a type of feature engineering which may require some special thought. There are multiple different ways to treat missing values, and that depends on the context, whether, for example, you want to treat missing value as a special category, or you just want to, for example, use existing information in the data to replace this. So for numerical features, if you have binary, so if you have two values plus a missing value, you may indeed consider to treat the missing category as a separate feature. For tree-based methods, if you intend to use tree-based methods, then you might as well replace the missing value with something very high, something that exceeds the range of the given feature, because then you make it easy for tree-based algorithms to isolate these values and essentially apply special treatment. Or you can actually create a new feature that says this is a null value, especially if you want to use neural networks or linear models. And you can still replace with the mean or mode or median the missing value. So just to illustrate this, if you have a binary feature, as you can basically say that one value remains as 1, the 0 feature will be recorded to -1, and the none feature gains a new value, which is 0. And for the numerical feature, what you can do is replace, for example, with 2 times the max value. So now you have a value which is very outside the range of the rest. So an algorithm like LightGBM or XGBoost will be able to isolate this and treat it in a special way, potentially in its own bin. Or another way to do it is replace, for example, with the mean value, but then generate a new feature that says this value is none or not. And sometimes this feature is not necessary, but some other times it might add some value. So it may be that just replacing with the mean is enough, but in some cases, also telling the algorithm that this was originally none can be a useful information in order to extract a bit more accuracy. For categorical features, you can treat the missing value as a separate category. Or, for example, you can replace with the mode, so with the most popular category in the data. A appears more times, so we just replace with A. Again, it's tough to know which is the best way to do this. I personally treat this as a hyperparameter, so I will iterate through these different techniques and try to find the one that works best with my data. Again, having a holdout data set. So features, interactions. I can see there are some questions, but I'll try to answer them at the end. I'm a bit cautious about the time. Feature interactions are when you try to combine two features in order to get a better, a stronger feature, a feature that contains more information. And one way to do that is through mathematical operations. For example, multiplying, adding two columns, subtracting, dividing, or other mathematical operations. A different way to do this is if you have two categorical columns, you can just concatenate them and then treat them as how you would treat a categorical field. So you can try all these different categorical transformations you saw before. And you can still do interactions if you have a categorical and a numerical feature. One way to do it is with similar to the target encoding that we saw before. So you can create some group by features, for example, calculate average age. And you don't need to limit yourself to average. It can be maximum standard deviation or other aggregated functions. And you can then basically replace with these values. Or you can first bin age and make it categorical, and then treat it as two categorical columns combined together. And any of these things could work. And sometimes multiple of these things work. You may have, you know, 2 ways to do the interaction. It may still be adding value. Again, you need to have a holdout data set and try. And the one way to do this is you can just loop through all possible 2 ways interactions, or you can get an inspiration by using a decision tree. A decision tree will be able to tell you that, you know, after you split feature 1, then you look at cutoffs for feature 2. So then you can understand if there is an interesting interaction between 2 features that you can potentially look at and create this type of interactions. Time series has its own feature engineering. Some simple things you can do is, if you have a date, you can decompose it into each element, creating fields like which day, which month it is, which week number. And you can even create fields like, is it a bank holiday, which sometimes tend to be predictive. And there are available packages out there that can help you do that. Other type of features is using past information from the target or from other features. So primarily creating lag variables. So if you have the target, you can use the value of what happened yesterday, 2 days ago, 3 days ago, lag 1, 2, or 3 as features in order to try and predict what's going to happen in the future. And you don't need to limit yourself to single lags. You can take combinations of lags. For example, you can take what we call a moving average of the last X number of observations, which quite often tends to be a bit more predictive, contains more information, is a bit more robust than single lag features. And you can even try to create a weighted version of that moving average where you put more weight into what happened more recently. And you can do this with a linear, you can have a linear decay, or you can do this with an exponential decay, so that the most recent lag feature, the most recent observation is exponentially more important than the one which is further in the past. And again, tough to know which things is the best unless you actually try it out and see what works better. And when you create these windows, you don't need to limit yourself to, for example, moving averages. You can, you know, take standard deviation, maximum values, any form of aggregated measure or descriptive feature can actually help. You can also create interactions. So instead of just, you know, taking the average or the lag values as they are, you can try and create things like lag 1 minus lag 2. And this can help to remove the trend and focus more into day-to-day fluctuations. And there are multiple ways you can create these interactions. For example, you can add or divide or subtract, and you can even take a moving average of these interactions, of these differentiations, and you can try to interact different lags together as well. It doesn't need to be lag 1 minus lag 2, it could be lag 1 minus lag 3. Again, this is something that you find through experimentation. Quite difficult to immediately pick this up by looking at the data. Through experience, obviously you can come up with shortcuts to do this quicker, but at the end of the day, you want to be able to have a testing framework where you can try a lot of these things and see what actually works better. Another type of feature you can use is a form of trend, try to capture the trend, which may be fitting a linear regression versus time for the past lag values, trying to predict the lag values. So then you can sort of understand the slope. Like you can use actually the regression coefficient, or you can just run a simple Pearson correlation, and you can see the slope, whether there is a tendency for the series to go up or down, and how strong that tendency is. And this can be a strong feature for some problems. And then you can also have some univariate transformations where, for example, you can take the square root of the target or natural logarithm of the target. And this can help with outliers. Time series problems can be more sensitive to outliers. Depends also what you're trying to optimize. you try to optimize, for example, for a root mean square logarithmic error, you most probably need to use logarithm in your target. Or you can actually use differentiation that you saw before. If instead of just predicting the target, you can predict the target minus a lag value or minus the average of the previous lag values. And this can be, again, quite powerful because it removes the trend. You can focus more into day-to-day fluctuations. You can extrapolate better, especially with certain techniques. Very briefly, I would like to mention about NLP and images. So with text, one thing you can do is decompose the text into tokens. And you can do that using a technique called, for example, the term frequency matrix, which can also take a different form, adding the inverse document frequency matrix. And what this does is it takes each word and basically treats it as a single column in your data. And then you count out of all possible words in your data, which words and how many times appear in each row. And sometimes this representation is powerful enough for a linear algorithm or an XGBoost model in order to give you some good predictive results. And because the dimensionality can be quite large, so the number of distinct words can be quite large, you can then use some techniques to reduce that. But before doing this, you can actually do further things on the words. For example, you can apply stemming, which is essentially removing the suffixes of the words. For example, playing or played will become play. You will just use the root of the words. You can use spell checking, so removing potential errors. You can remove stop words, some words that don't add much context. They're just there to blend the whole thing together. You can use translations. This is a good way to augment your data if you don't have much. For example, you have a sentence, you can translate it to another language, and then you can translate it back. And that translation, because it's not perfect, you might get something different. And that way you can generate more samples in order to fit your algorithms. So once you then create this matrix, quite often you want to reduce it. And you can do it with singular value decomposition, which is like principal components, or you can use a word to vec type of transformation. And the way this works is it's a type of deep learning model that once trained, it replaces, it maps each word to a sequence of numbers in a way that you can do mathematical operations between words. For example, if from the word king you subtract the word man, the result could be the word queen. It doesn't always work so nicely, but there is a lot of information in there in these numerical vectors that you can extract a lot of value about what the text is about. And you don't need to train your own vectors. You can get some vectors, some embeddings which are pre-trained. For example, Globe and FastText has, and they have been trained in some massive corpuses of data. And there are many other transformers available in this Hugging Face Python package and NLTK. I do advise people to have a look. And also you have some models that basically incorporate feature engineering internally, like the BERT models. Images. There are many things you can do with slightly changing the image. For example, you can try flipping it horizontally, vertically, zoom in and zoom out along with rotates, and other type of adding some distortion, some gamma or some brightness. So ways to change the image a little bit so that the algorithm can basically will overfit less and can also learn different patterns. I like to use a package called Albumentations from Python, which has a lot of these transformations. And generally, they're normally very, very critical to giving you better results. And then there are also many deep learning models like ResNet, efficient nets that are pre-trained on some data sets, for example, ImageNet, and using these pre-trained models quite often can make your modeling procedure much faster and quite often to convert to better results. These are some of my favorite packages. So for deep learning, I like to use these both for modeling as well as for feature engineering. For NLP, I like these three packages: Hugging Face, NLTK, Gensim. For general transformations, very general feature engineering, some of text and some of the encoders like label encodings, one-hot encoding, or binning, scikit-learn, H2O have very good functions. And then for the rest, data frame manipulation, data table, and pandas, and NumPy and SciPy contain a lot of other functions for arrays, for example, to help you with the feature engineering. This is what I wanted to cover. Let me see some of the questions. Which is best encoding for recommendation systems where all the features are categorical? So for recommendation systems, quite popular is to actually use some form of embeddings, to use some form of SVD and PCA, but not necessarily in that format. For example, people tend to use a model called libfm, which may take some of the interaction between two categories and try to summarize this in another dimensional space. For example, you can create some factor features. It's very similar to factorization in a sense, and this is very, very popular in recommender systems. So instead of just using the category, you represent each category with a series of numbers, like what I showed you before with word2vec, and then you can basically take the product of these vectors in order to create one score for how a product, for example, could be linked to a customer. So I do advise you to look into factorization machines and libfm if you want to see some interesting ways for recommender systems. Please clarify if you can use some of the previous techniques, such as introducing noise, to help us with the time series data. Yes, we can use this. It is actually quite common to add noise, time series, or signal processing type of problem. You may see things like low pass filters, and they exactly serve this purpose in order to take away the noise. Even the moving average itself tries to take away some of the noise that may be embedded within the single lag features. Even physically adding some noise in lag values can sometimes yield, as in Gaussian noise, can quite often serve as regularization and give you better results. So yeah, you can definitely do that. And with this, I think I covered what I wanted to say. Do I have any more time, admins? Can you help me with that?
Yeah, Mario, so feel free to take a little bit more time. This is all recorded, so folks can listen to the replay.
Right, so what I wanted to very quickly say as a bonus is, as I mentioned before, one way to understand how good a feature is seeing the results in the validation, in some holdout data. But it can be tricky. Sometimes you may be adding a bunch of features and you may actually be seeing performance but uplift, but it may be that not all of them are important, and it may take a lot of time to try only one feature at a time. So normally we create a bulk of features, like a bunch of them, and then we evaluate them all together. And one way where you can quickly assess which features are good is through using this feature ranking based on permutations. And the way this works is, let's say that's your training data set, you have 4 features and 1 target column. You can separate it into training and holdout and validation. You can then feed an algorithm. It doesn't matter what it is. This technique works with any algorithm, but let's say For this case, it is like GBM. So you can fit the algorithm in the training data and then make predictions in this holdout data set. And this can give you an X percentage of accuracy, let's say 80%. So what you can do next is take the first feature in your validation data and randomly shuffle it. So change the order for that feature. So you maintain the same distribution, but it is a random feature now. I've changed the order. So you have one feature that is wrong, and every other feature is correct. And then I repeat the scoring, only the scoring, with the same model. And once I do this, it will give me a new accuracy, which let's say 70%, there is a drop. So the difference between the two, in this case, that 10% difference, is how important that feature was. And you can create a ranking in this way, then you can bring this back to normal, back to the original order, and then you move on to the second feature. And then only the inference, only the prediction is repeated multiple times, but you've trained your model only once. And then you have a ranking with which features are the most important. And if you create many, many features, like hundreds of features, you will be surprised that after you do this ranking, some of the features will give you better accuracy after you randomly shuffle them. So after being wrong in the data, which means that these features were just noise. And this can actually happen quite a lot if you aggressively try to create many features. And this is something that I generally do. Because there are many things that I want to try, I create a big bunch of features each time. And I know I tend to evaluate them in this way. And then I see which of them decrease, like improve my accuracy when I randomly shuffle them, which they shouldn't do this, or they give me very, very minimal drop into the original accuracy. And then I remove them and I repeat, and I see that indeed the accuracy improves. And this is a way to trim down the features after multiple iterations and see which ones actually added the most value. Is order of features important for training the model? Normally it shouldn't. Depends, I guess, what model you might want to use. I cannot think of a case where this I mean, the order of rows can matter. If we're talking about rows, it can matter because some algorithms that stream your data, it may be that, you know, if you have, you know, a specific order in how your rows, how your data set is sorted, it may be that it picks up, you know, some different information at the beginnings. It may be trapped to some local minima. That's why we tend to shuffle them. But for columns, it's not something I have seen. I could make a case that on a very, very, very rare occasions for a small data set, it may have like an extremely minor impact, but generally, I don't think so. It's not something you should worry about. Another question, is there anything in H03 or driverless AI to do feature ranking based on permutation? Driverless AI does use different feature, it uses similar approaches, may not exactly the same, but the same logic. Like when you remove a feature and then you repeat the scoring and see how the prediction changes. It may not be directly in relation to accuracy, for example, but we have multiple techniques in driverless AI that can do this. So yeah, and we have many other feature selection methods as well, or other ways to assess how important a feature is. For example, you can do it with the decision trees. You can see how the criterion improves every time you split. And other techniques as well. In the linear models, you can see things like the p-values, for example. And there are other metrics as well. Is there any package for ranking the features? There might be, to be honest. I'm not aware because I prefer to do this myself. There might be. Actually, let me come back on that at a later point. Generally, this is something I like to do. I like to do myself, so I'm not aware. But they might as well be. I mean, there are definitely features to help you do techniques to help you do feature selection. Scikit-learn has, for example. But specifically on permutations, I'm pretty sure there should be something. It's not something that I use, so I will need to come back on that. So we are using, another question, we're introducing deliberate noise as means of determining the robustness of the models to identify outliers or anomalous low significance data. I'm not sure you can do it to identify outliers, but you can definitely make your model more robust to different values. You don't have only one way, especially if your data set is small. Being able to change a bit the input can give your algorithm more options. Yeah, is able to handle if you give a slightly different value in the validation data, in the test data, a value that was not present in the training data, if you're able to shake up things a little bit in your training data, then you do extend that ability of your model to see values outside the range, or not necessarily outside the range, but to be able to see more combinations. So it's more resilient, especially if you try to score it with something. If you try to challenge a model with something which is new. So yeah, you do make the model more robust. I think these are all the questions. Well, thank you for bearing with me. Also happy to take any questions offline. Yeah, thank you very much for your time. I hope you found it useful. I'm always reachable through LinkedIn, for example, or by email, which I forgot to add in the last slide. Apologies for that. I will send the information later. But yeah, thank you very much.
Thank you, Marios. Thank you for a very interesting session. So like most of our sessions, the recording and the slides will be posted within about 24 hours. So folks can be able to check out the replays there. Our next session will be on Thursday at the same time to take our next steps into feature engineering. So thanks again, Marios and everyone for joining. And we will see you at the next session. Thank you. Have a good day.